Why does Europe's weather keep doing this? Why does the continent lock into these brutal, weeks-long heat waves that bake the land dry and then sometimes break into sudden violent floods? It's not random, and it's not bad luck. The answer is written in the sky, specifically in the shape of a fast-flowing river of air miles above our heads called the jet stream. And right now, that jet stream is contorting itself into a very specific, very stubborn pattern that meteorologists have a name for, an omega block. It's the atmospheric machinery behind the big change now unfolding across Europe. The returning heat dome, the sharp north-south split, the storms at the boundaries. So today, instead of just telling you what's coming, we're going to explain why it's coming. We're going to break down the actual science of this pattern change. The jet stream, the blocking high, the omega block, and the forces locking Europe's weather in place. Because once you understand the machinery, the whole picture suddenly makes sense. And I'm going to give you the real science, explained clearly and without the hype, because understanding why the weather behaves this way is genuinely more useful and more fascinating than just reacting to the headlines. So let me give it to you straight. But before we dive in, do me one quick favor because it genuinely helps this channel. Drop a comment right now and tell me where you're watching from and whether you'd ever heard of a blocking pattern or an omega block before today. Most people have no idea these have names, let alone that they explain so much of our weather. And if you love understanding the why behind what's happening in our skies, hit that subscribe button. It's free, it takes 1 second, and it means you'll always get the real explanation. A wide thumbs up helps push this out to more people who deserve to understand it. All right, let's get into it. To understand everything that's happening, we have to start with the jet stream, because it's the master conductor of weather across Europe and the rest of the mid-latitudes. So what is it? The jet stream is a band of very fast-moving air high up in the atmosphere, where the cold air of the polar regions meets the warmer air of the tropics. That temperature contrast, combined with the Earth's rotation, generates a powerful current of wind that flows generally from west to east, around the globe, snaking its way across the planet. And here's why it matters so much. The jet stream acts like a steering wheel for weather systems. It guides the areas of high and low pressure, the sunny spells and the rain-bearing storms along its path. When the jet stream is flowing strong and relatively straight from west to east, weather systems move along briskly one after another, giving us that changeable, nothing lasts too long kind of weather. A few nice days, then some rain, then nice again. The weather keeps moving because the jet stream keeps it moving. Let me add a bit more about this remarkable river of air, because its scale is genuinely awesome. The jet stream flows at altitudes of around 10 kilometers up, roughly where airliners cruise, which is why flights from west to east across the Atlantic can be significantly faster than flights going the other way. Pilots ride the jet stream like a tailwind. The winds within it can howl at well over 100 miles per hour, sometimes approaching 200. And it exists fundamentally because of temperature contrast. The sharper the difference between the cold polar air to the north and the warm subtropical air to the south, the stronger and tighter the jet stream tends to be. In winter, when that contrast is greatest, the jet stream is typically strong and fast, driving vigorous weather. In summer, when the contrast relaxes, the jet stream tends to be weaker and can become more prone to those big, lazy, meandering waves. And that summer sluggishness is part of why blocking patterns and the prolonged heat waves they bring are so characteristic of the summer season. A weaker, wavier summer jet stream is simply more likely to get stuck. So the very time of year when heat is most dangerous is also the time when the atmosphere is most prone to locking that heat in place. But the jet stream doesn't always flow in a nice straight line. Sometimes it develops big, sweeping waves, huge northward and southward meanders like a river winding across a plain. And when those waves get large enough and slow enough, something dramatic can happen. The pattern can get stuck. The waves stop progressing eastward and lock into place. This is what meteorologists call a blocking pattern. And it's the key to understanding prolonged extreme weather. Because when the jet stream gets blocked, the weather systems it normally steers along get stuck too. A sunny high-pressure system that would normally drift past in a day or two, instead parks itself over a region and stays there, for days, for a week, sometimes for much longer. The weather stops changing, and that is exactly how you get a prolonged heat wave. Not from a single hot day, but from a hot, high-pressure system that gets stuck in place and refuses to move, baking the same region day after day after day. Now, let's get to the specific and rather elegant pattern behind the current situation, the omega block. It gets its name because the shape the jet stream traces out looks just like the capital Greek letter omega, that horseshoe or upside-down U shape. Picture it. The jet stream sweeps way up to the north in the middle, forming a big dome, and then plunges back down to the south on either side. In the middle of that dome sits a large, strong area of high pressure, a ridge, and on each flank, where the jet stream dips south, sit two areas of low pressure. So the structure is A big, high-pressure ridge in the center, flanked by two low-pressure systems, one on each side. That whole arrangement traces the omega shape, and it is a remarkably stable, stubborn configuration. The two flanking lows essentially act like doorstops, holding the central high firmly in place and preventing it from moving on. That's why an omega block can lock a weather pattern in for a long time. The omega block isn't the only kind of blocking pattern, and it's worth briefly knowing its cousins, because it helps you appreciate what's special about it. A high over low arrangement that also stalls the flow and can split the jet stream. There are also cutoff lows, which are exactly what they sound like. Pockets of low pressure that get pinched off and left behind, isolated from the main jet stream flow, where they can spin in place for days, bringing persistent rain and storms to one area. Often, in fact, those very flanking lows of an omega block can become cut-off lows. What all these blocking patterns share is that they disrupt the normal, orderly west-to-east progression of weather and replace it with something stuck and persistent. The omega block, with its distinctive high flanked by two lows structure, is among the most recognizable and the most effective at producing that classic combination of a stubborn central heat dome and stormy conditions on either side. And once you learn to spot that omega shape on a pressure map, you'll start seeing it behind many of the continent's most memorable heat waves. And this maps precisely onto what's happening over Europe right now. The forecasts describe exactly this setup: a strong high-pressure ridge, the heat dome, parked over the heart of the continent, with a deep low-pressure area out over the North Atlantic on one side, and another low over Russia on the other. That's a textbook omega block, with Europe's heat sitting right under the central ridge. And now you can understand why the weather splits the way it does, because each part of the omega produces very different conditions. Under that central high-pressure ridge, you get the heat. Here's the mechanism. Within a high-pressure system, the air is sinking, and as air sinks, it compresses and warms up. Sinking air also suppresses cloud formation, leading to clear skies and abundant sunshine. So under the ridge, you have warming, sinking air, and relentless sun baking the surface day after day. The perfect recipe for building extreme heat and deepening drought. That's why the regions under the ridge, southern and central Europe right now, roast. But under those two flanking areas of low pressure, it's the opposite story. Low pressure means rising air, which cools and condenses to form clouds and precipitation. So the regions near the flanking lows get unsettled, cooler, stormier weather. This is the key insight. A single omega block simultaneously produces extreme heat and drought in one place and cool, wet, stormy conditions in another, all at the same time, all part of the same locked-in pattern. That's precisely the divided continent we're seeing. Baking heat in the south and center, cooler and more changeable conditions toward the northwest, and turbulent boundaries in between. History offers some sobering examples of just how deadly these blocking heat patterns can be, which is why meteorologists take them so seriously. One of the most infamous was the European heat wave of 2003, when a powerful, persistent blocking ridge parked over the continent for weeks and drove temperatures to extraordinary levels across France and much of Western Europe. That single event is estimated to have contributed to tens of thousands of deaths, one of the deadliest natural disasters in modern European history, and it fundamentally changed how European countries prepare for and respond to extreme heat. Another stark example struck in 2010 when an enormous, stubborn blocking high settled over western Russia, producing a catastrophic heat wave and drought that fueled massive wildfires around Moscow, blanketing the city in choking smoke and causing a staggering death toll, while at the very same time, on the flank of that same block, devastating floods struck Pakistan. That's the signature of these blocks writ large: extreme heat in one place and catastrophic flooding in another, both driven by the same stuck pattern. These historical events are a powerful reminder that a blocking pattern isn't just a meteorological curiosity. It can be a genuine large-scale disaster, which is exactly why forecasters watch so carefully when one sets up, as it is over Europe now. There's another piece of the puzzle that's shaping the northern side of this split, and it has its own name, the North Atlantic Oscillation, or NAO. The NAO describes the seesawing relationship between pressure systems over the North Atlantic, and it has a big influence on European weather. Right now, forecasters have been noting the development of what's called a negative NAO phase. In simple terms, a negative NAO tends to be associated with a change in where the high pressure and the jet stream set up, often favoring more ridging and blocking to the northwest of the UK. This can push the main storm track and the jet stream around in ways that, combined with the omega block, reinforce that pattern of cooler, drier, or more variable conditions across the north and northwest, while the heat dominates further south. So the negative NAO and the omega block are working together to sculpt this particular configuration of Europe's weather, the specific fingerprints of which regions bake and which stay cool. Now, here's a genuinely important and timely question. Are these blocking patterns becoming more common? Because it certainly feels like Europe has been hit by one stuck extreme pattern after another in recent years. And this is an area of very active scientific research. So let me give you the honest, balanced picture. There's real evidence that these persistent, locked-in weather patterns, the kind that produce prolonged heat waves and flooding, have been occurring more frequently. In fact, a scientific study published recently found that the atmospheric patterns that lock in extreme weather, such as heat domes and persistent flooding setups, have nearly tripled in occurrence. That's a striking finding, and it aligns with the lived experience of these repeated, stuck extremes. The deeper question is why, and here the science is still being actively worked out. So I'll be careful to represent it fairly. One leading hypothesis connects it to the warming of the Arctic. The idea goes like this. The Arctic has been warming faster than the rest of the planet, which reduces the temperature contrast between the pole and the mid-latitudes. And since that temperature contrast is part of what powers and shapes the jet stream, some scientists propose that a weaker contrast could lead to a slower, wavier, more meander-prone jet stream, one that's more likely to get stuck in those big, blocking omega-type patterns. It's a compelling and intuitive idea. However, and this is important for honesty, this remains an area of genuine scientific debate. Not all researchers are convinced the link is that simple or that strong. The atmosphere is fantastically complex, and disentangling natural variability from longer-term trends is genuinely difficult. So the fair way to put it is this. Blocking patterns appear to be happening more often. There are plausible scientific mechanisms connecting that to a warming world, but the precise cause and effect is still being researched and debated. What's clearer is that whatever the exact mechanism, the consequences of these blocks, when they set up over an already warmer world, tend to be more extreme because the same stuck pattern now bakes a baseline that's hotter than it used to be. Let me add a bit more nuance to that debate because it's a genuinely fascinating scientific frontier. The core of the disagreement is this. The atmosphere has always produced blocking patterns. They're a completely natural. So the question isn't whether they're natural. They are. The question is whether a warming world, and a warming Arctic in particular, is nudging the odds toward more of them or more persistent ones. Some studies find evidence pointing that way. Others caution that the natural year-to-year variability of the jet stream is so large that it's hard to statistically prove a trend, and that different climate models don't all agree on how the jet stream will respond to warming. Both camps are doing rigorous science. They're just wrestling with a genuinely hard problem at the edge of what current data and models can resolve. What most researchers do agree on is the simpler, more robust point I mentioned. Even if blocking frequency didn't change at all, the heat waves these blocks produce are landing on a warmer baseline, so they reach higher temperatures and cause more harm than the same pattern would have decades ago. That part isn't really in dispute, and it's reason enough to take these events seriously. And that connects to another amplifying factor worth understanding, the feedback loop between the drought and the heat that these blocks create. When an omega block parks a heat dome over a region and bakes the ground dry, that dryness itself intensifies the heat. Here's why. Moist soil uses some of the sun's energy to evaporate water, which has a cooling effect. But once the soil is baked bone dry, as it is across much of Europe right now after this long summer, there's no moisture left to evaporate, so all of the sun's energy goes directly into heating the air. The dry ground makes the heat worse, which dries the ground further, which makes the heat worse still. So the blocking pattern and the drought reinforce each other, and a heat dome setting up over already parched European soil, as is happening now, can produce even more intense heat than it otherwise would. It's another reason this fourth heat wave landing on a drought-stricken continent is so concerning. So let's step back and appreciate what all this science tells us about the big change unfolding across Europe. It's not chaos, and it's not random. It's the product of a specific, recognizable, and well-understood atmospheric configuration. An omega block, reinforced by a negative Neo phase, locking a heat dome over southern and central Europe while leaving the northwest cooler and more unsettled, with turbulent boundaries in between where storms can erupt. That block is holding the pattern stubbornly in place, which is why the heat is forecast to persist and expand rather than quickly passing. These blocks appear to be occurring more frequently, likely amplified by a warming world, and their effects are magnified by the drought feedback that dries and heats the land in a vicious cycle. Understanding this is genuinely empowering because it transforms the weather from a series of scary, inexplicable events into a comprehensible system. When you hear heat dome or blocking pattern or omega block, you'll now know exactly what's happening up there and why it produces the weather we feel down here. There's an interesting wrinkle in how these blocks affect weather forecasting itself, and it's worth understanding. In one sense, A blocking pattern actually makes the forecast easier and more confident for a while. Because the pattern is stuck and persistent, forecasters can say with reasonable confidence that the heat will continue day after day, since nothing is moving it along. That's why you'll hear meteorologists forecast a heat wave lasting a week or more with real confidence once a block is established. But there's a catch. The moments that are genuinely hard to predict are the onset, and especially the breakdown of the block. Exactly when and how a blocking pattern finally collapses, when the jet stream breaks free and the trapped weather system is finally flushed away, can be notoriously difficult to nail down more than a few days in advance. So forecasters can often tell you a heat wave will persist, but pinning down the precise day the relief arrives, and how stormy that transition will be, is one of the trickier challenges in the business. This is exactly why, even with a well-understood pattern like the current one, there's genuine uncertainty about the later stages of the forecast, and why watching updates as the situation evolves matters so much. Here's the honest bottom line. Europe's weather is changing in a big way because the jet stream has buckled into a stubborn omega block, a high-pressure ridge trapped between two lows that's locking a heat dome over the south and center of the continent, while a negative NAO keeps the northwest cooler and changeable. This is a classic, well-understood pattern, not a mystery, and it explains the returning heat, the sharp split, and the storm-prone boundaries all at once. What's less certain, and genuinely debated among scientists, is exactly why these blocking patterns seem to be striking more often, though the evidence that they've increased is real and a warming world plausibly plays a role, and the drought-heat feedback loop only sharpens the extremes. Machinery behind it, the winding, stuck jet stream overhead, writing the shape of an omega across the sky. Understanding that is the difference between fearing the weather and comprehending it, and comprehension, as always, is the better path. I'm going to keep exploring all of it, the science of these patterns, the jet stream, the blocks, and everything that helps us understand the forces shaping our weather. If you want the calm, accurate explanations instead of the internet doom machine, subscribe so you don't miss an update, because understanding the why is what makes all of this genuinely make sense. Hit that like button to help this reach more people who deserve the real explanation instead of the hype. And drop a comment. Where are you watching from? And had you ever heard of an omega block before today? Tell me. I read every single one, and I'll see you in the next one. Stay curious out there, keep looking up, and remember, understanding the sky is always better than fearing it.